Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In our next lesson, we are going to look at acids and bases, as well as neutral compounds, because we're going to start acid-base equilibrium. So the main focus of this lesson is really what is an acid, what is a base, what makes it strong, what makes it weak. But before we can actually get to that point, you need to know what something that is neutral is, so that you can kind of disregard it from the fact that it is not an acid or a base. So I break in solutions into four major groups, and the first two are neutral. So we're going to first look here at neutral ionics and talk about how you can recognize them. So first of all, neutral ionic compounds are generally going to have one of 5 anions. So it could have perchlorate, nitrate, chloride, bromide, and iodide. Now, these 5 anions are actually what we call the conjugate bases of strong acids. Now, those are new terms to you, but let me write out the list of strong acids so that you can recognize that these have something to do with strong acids. So our 6 strong acids are HClO4, perchloric acid, HNO3, nitric acid, HCl, hydrochloric acid, HBr, hydrobromic acid, and HI, hydroiodic acid. Now there is a 6th here, which is not up on this list, and I'm going to write it in a different color, red, because it is very acidic. H2SO4, sulfuric acid. Its conjugate base, I'm going to write Cb as conjugate base, is HSO4 minus. This thing is very acidic, and therefore it would be an acid and not be part of our list. So the anions of 5 of the 6 strong acids will make a neutral solution when paired with a group 1 or group 2 metal cation. Now, there are always some exceptions to this rule, but the reason that we keep with group 1 and group 2 metal cations with these 5 as neutral ionic is because some of the transition metals can be quite acidic, and that goes beyond the scope of our current course. So this is what we stick with in terms of what is a neutral ionic. A neutral ionic will be a group 1 or group 2 metal cation with one of these 5 anions, and these 5 anions are the anions in 5 of the 6 strong acids. So examples like sodium nitrate has nitrate. Sodium is a group 1 metal cation. Sodium chloride. Chloride is one of the 5, and sodium is a group 1 metal cation. Potassium bromide. Bromide is one of the 5, and potassium is a group 1 metal cation. Again, there are other neutral ionic compounds, but we don't want to go outside of this basic concept of group 1 or group 2 with these 5. Next, we'll look at neutral molecular compounds. There are many neutral molecular compounds, but we're just going to memorize a few of them. So the 3 that you really kind of need to know at this level would be alcohols like methanol and ethanol. These are organic compounds and they are not acidic or basic. Sugars like glucose or sucrose, and pure water. Now we're going to learn that water can act like an acid or a base. It actually is the most common acid and base on planet Earth. However, pure water on its own is neutral and is not acidic or basic. The big problem most students have recognizing is when it comes to the alcohols. So when I have something like methanol, CH3OH, a lot of students think, and it's incorrect, a lot of students think that this is hydroxide. And it's not. Hydroxide is OH minus, which is an ion, And the OH in this compound is actually called a hydroxyl group, which is an organic group. And it does not split off the CH3 to form OH minus because these things are covalently bonded. And therefore they do not form ions. So one more time, the most common misconception is that alcohols are basic. Most people recognize that hydroxide is a base. However, these OH groups are really called hydroxyl groups. They're covalently bonded to this compound, and they do not split off as an ion. If they did, we could not drink ethanol alcohol without pretty much killing ourselves. It would be drinking strong base, which it obviously is not. There are many definitions of acids out there, including the Arrhenius, modified Arrhenius, and a Bronsted-Lowry theory of acids and bases. In this course, we look exclusively at the Bronsted-Lowry acid definition, which is actually very simple. A Bronsted-Lowry acid is a proton donor, or basically gives up a proton. Now, that might seem funny, proton. Proton's something you find in the nucleus of an element. What does that have to do with being an acid? Well, most people already at this point know that H plus is acid, or more formally, actually hydronium ion is acid. What they don't recognize is H plus is a proton. An H plus ion is only a proton. They are actually the exact same thing. So when you look at an atom of hydrogen, all it is one proton and one electron. There is no neutron in a hydrogen atom. So when a hydrogen atom ionizes and loses that electron, what's left is simply just a proton. That's all that's left. A proton is H plus. They are exactly the same thing. So I hope this helps you recognize that things like HCl, which have a hydrogen that can ionize, or HI or HBr, they all have a hydrogen atom that can ionize and turn into a proton. And therefore, these things are classified as acids because they can donate a proton. So what I'd like to look at first is the ionization of hydrogen iodide, which is a strong acid. This is a strong acid with water. So looking at these diagrams, what I'm going to do is fill in what everything represents. This would represent an I, and this would represent an H, H, O, H, and so on. This would be I minus, and this would be H3O plus. So HI itself actually isn't acid. We call it acid because when you put it in water, it acts as an acid and donates a proton to water 100% of the time. That's what makes it a strong acid. Now let's look at what would happen at the molecular level. If we were to look at the polarity of HI, this would be a very negative part of the molecule, and this would be a very positive part of the molecule. Now, if you were to look at water, water would be very negative around the oxygen and very positive around the hydrogens. So what happens is when you dissolve HI in water, and it does dissolve because it is polar, it will actually bump into waters constantly. And when it does this at the right angle, where a hydrogen can actually hit into this lone pair of electrons, this hydrogen will actually jump ship and stick to those electrons, forming the H3O ion, which is called hydronium, which is acid. So one more time, This positive hydrogen is attracted to this negative oxygen. It donates its hydrogen to those lone pair of electrons. These electrons that are here, which is a pair, are left behind. Those are these two electrons on I minus. The hydrogen leaves only as a proton and piggybacks onto this lone pair of electrons, making the H2O now H3O plus, which is acid. So again, to clarify, this hydrogen goes to this spot here 100% of the time if you have a strong acid. And because of this, there is no equilibrium arrow because this is not in equilibrium. We would call this a quantitative reaction, which means it goes 100% forward. Now, if you're wondering, what does Ka thing represent up here? Ks are used in equilibrium to represent how far forward this reaction goes. And because this is essentially 100% forward, this is really an infinitely large value. In our data books, it simply just says very large because a K value is the concentration of the products over the concentration of the reactants. And there really is virtually none of the reactants left. And therefore, you have an infinitely large value on top. So we wouldn't even say this is in equilibrium. This is so far to the right. This is not an equilibrium equation. So in Chemistry 20, you would have dealt with a lot of strong acids exclusively in calculations because we wouldn't need an ICE table to solve for concentrations because it quantitatively goes 100% forward. And they are always balanced 1 to 1 to 1 to 1. So for instance, if I know the concentration of HI to start was 1.0 moles per liter, then I know that this is also the concentration of I minus, because as a mole to mole ratio, it's 1 to 1. And I actually also know that the concentration of H3O plus is 1 moles per liter. And you may have done a quantitative calculation like something like pH is equal to the negative log of H3O plus. So since HI ionizes 100% to make H3O plus, and this was 1 moles per liter, that makes this 1 moles per liter. And if you were to take the negative log of 1, that's a pH of 0. Any concentration of a strong acid over 1 will actually give you a negative pH value, which is 100% allowed. Acids can go quite negative, and bases can go over 14, just not generally in household acids or bases that you would find. The final thing I would like to show you is the major species involved in the ionization of a strong acid. So looking at this beaker on the right, we can see that the reaction goes 100% forward. If I had a beaker labeled HI, there would be no HI present. Because it reacts with water 100%, it's going to turn 100% into products, and they should be relatively the same amount of each. So for instance, I have 5 hydroniums here. I have 6 iodides. I probably should have 5 because if it was a 1-to-1 ratio, I'll add in 1 more hydronium. But I have no reactants. So I would say that the major species involved is H3O plus and I minus. This is true for all strong acids. All strong acids ionize 100%, and all of them have the major species of their products, which would be H3O plus and their conjugate base. In this case, the conjugate base would be the I minus. Compared to strong acids, weak acids ionize less than 100%. So a weak acid ionizes less than 100%. And to be honest, realistically, most would react less than 5%. And their K values, in this case, we call it a Ka value, which is the ionization of a weak acid, is going to be really less than 1, which means they're really going to favor the reactant side of the reaction. And we could say that the reaction is less than 50% forward. So let me explain this whole Ka situation by starting out that K values are K values. Putting a subscript of an A is just giving you something that is more specific to a certain type of equilibrium. The A for Ka is just for acid. So when we're writing a Ka expression, it's always going to be products over reactants. So if I was looking at my HF ionization at the top of the page, my products would be F minus and H3O plus. Now that would all be over my reactants, but my one reactant is water liquid and wouldn't be included, so we would write HF. So this would be the Ka expression for HF, which is a weak acid. But I would also like to show you what the generic one would look like. So a generic Ka for an acid such as HF would be A minus times H3O plus, and this is all over HA. So what does this A minus and HA represent? The A minus represents the conjugate base or the anion that's formed when you react with water. It's just a generic monoprotic weak base, A minus. So this represents here a conjugate base. This is also a conjugate base, and I will show you where you can find those in just a moment. The F minus on the bottom, or HA, those basically represent the same thing. They represent the weak acid. And in the case of HA here, this would actually be called a weak monoprotic acid. Mono meaning one, protic meaning hydrogen. It has one hydrogen. Monoprotic weak acid. Now, the actual molecular thing that happens in this reaction is very similar to above. It's the same philosophy or the same idea. If this was F and this was H, and this was O and H, what happens is when these collide, the H, which is positive, is attracted to the very negative lone pair of electrons. But here's the difference. This will be donated a small percentage of the time. Now, the stronger the weak acid is, I know that sounds weird. So I always think when I give a comparison between weak and strong is I talk about professional and amateur athletes, okay? A professional athlete is like a professional acid. It's strong. It's the best. But you can have amateur athletes that are really good at their sport. They're just not professional. So a strong weak acid would be like a very good amateur athlete. This percentage that they donate may be quite high, but it's nowhere near 100%. So some of the HF, some of the time will hit the water. And so this reaction is in equilibrium because we don't go 100% forward. This, of course, on the other side would represent F minus, and this would be H3O plus. Now, the Ka value can be found on charts in data books. In our chart, it would be 6.3 times 10 to the negative 4. And that value shows us that this reaction favors the reactants. It's less than 50% forward, and it goes this direction. HF at 10 to the negative 4 is still considered a fairly strong weak acid because it does donate a significant amount of H plus to water. Now, if I was to look at a beaker and this beaker was labeled HF, I would see tons and tons of HF. So you can see I've got HF, 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 HF. HF is extremely polar and it dissolves in water very well. But because the hydrogen holds onto the F so tightly, or I should probably see the F holds onto the H so tightly due to its very small radius and high electronegativity, it doesn't want to give up its H to water very readily. Therefore, it's going to be very hard or not very often that you would see an acid ion or its conjugate base of HF, F minus. So here we have a different set of major species. The major species is actually the reactants, which is HF, but I wouldn't include water because water is the solvent and it's everywhere. So the major species in a beaker of an acid which is weak is always going to be the reactants. And really the reactant is just going to be the molecule of acid. Now, some terms you should also know from previous chemistry courses are the terms monoprotic acids, diprotic acids, and triprotic acids. Protic just tells you the number of hydrogens, mono meaning 1, di meaning 2, and tri, of course, meaning 3. However, we often just lump diprotic and triprotic together into one single term. So the term that's used for diprotic and triprotic most often is called polyprotic. Poly, of course, means more than one. Like if you're into polygamy, you would have more than one wife. Weird. Okay, so monoprotic acids would include such things as HCl, HBr, HF, but it can also include organic acids which have a COOH group. So I could also have something like vinegar, CH3COOH. Now, if you're wondering and you say, but there's 4 hydrogens there, how could this be monoprotic? Only the hydrogen attached to the H on the end of the carboxylic acid group, which is this H there. This COOH is called the carboxylic acid group. Only this H can be donated because there's an extremely polar bond between the hydrogen and oxygen. These hydrogens, which are attached to the carbon group together, can never ionize. And therefore, this would be monoprotic only because it only has one COOH group. Another example would be something like formic acid, HCOOH. Only the H on the end of the carboxylic acid group would be able to ionize. This H here, which is directly bonded to this carbon, could never ionize because it's not a polar enough bond between the carbon and hydrogen. It's actually a completely non-polar bond. So again, a COOH group, if you have one of them, it's monoprotic. If you have 2, it would be diprotic. If you had 3, it would be triprotic. Examples of diprotic acids would be things like H2CO3, carbonic acid, H2SO4, H2S. Those are all diprotic. And there's a very, very common diprotic organic acid. I'm just going to write it on the end here, called oxalic acid. It's HOOCCOOH. What you'll notice is that it has 2 carboxylic groups, this one and then this one. And it also has 2 H's, this one and this one. Triprotic, of course, would be with 3 hydrogens. So H3PO4 is probably the most common one. You can also have citric acid. Citric acid is quite a large molecule. It's C3H5O COOH in brackets with a 3 on the outside, meaning that I have three H's on three carboxylic groups. This 3 would be those 3 there. So what Ka represents is an acid reacting with water. The reactions themselves are always going to look very similar in this fashion. It's always going to be something plus water forming its anion plus hydronium. What's underlined in pink would just be changed out. The water and the hydronium would always be constant. It's always going to be blank plus water, equilibrium arrow, blank plus hydronium. That is a Ka reaction. We just have to fill in those blanks with Ha, which is generic, and A minus, which is generic. The first one being the weak acid, and the second one being its weak conjugate base. Moving on to bases, we are going to look at a Bronsted-Lowry base, which is called a proton acceptor. Now, the definition of a proton acceptor doesn't really apply to a strong base, such as sodium hydroxide, which doesn't actually accept a proton. It actually just dissociates to form hydroxide. So please remember that what a base is hydroxide. So if something contains a hydroxide and dissociates, like sodium hydroxide, into 2 ions, which produces hydroxide, which is base, it's not actually accepting a proton to do this. It's just splitting up to create the hydroxide. Where the proton acceptor definition really comes into play is really with the weaks, which we're going to deal with next. So first I'd like to talk about what are the strong bases and what exactly are they doing. So if this was a sodium ion and this was a hydroxide ion, I'm going to put the negative on the outside because the negative applies to both the O and the H together. Because it's highly soluble, it will dissociate in water 100%, and this would not be considered in equilibrium. So this would be a sodium ion which is produced. This is neutral ionic. It's a group 1 metal. It has nothing to do with acid or base. It's just highly soluble. And this would be a O and an H, which would be negatively charged. So this is called hydroxide. And this is base. This really doesn't have a Kb associated with it at all because it isn't even a reaction. I can't even say the Kb is infinitely huge because it doesn't even react. It's just splitting into its 2 ions. So most strong bases occur like this in a 1:1:1 ratio. So 1:1:1 ratio. And so if I know the concentration of NaOH, is 1.0 moles per liter, then I know the concentration of sodium ions are also 1 moles per liter. But more importantly, I can know that the concentration of OH minus ions is 1 moles per liter. And therefore, I can use all of my simple quantitative values in equations like POH, POH being the negative log of OH minus. Okay, and of course, if I put that value in, the negative log of 1 is always equal to 0. So the POH would be 0 here. And then if I wanted to do the pH, it would be 14 minus that value, which would be 14. So this would be a very high pH, which is normal for a very strong base at high concentration. Now, there is no list for us to look up in terms of what is a strong base, so I'm just going to write it out here. Strong bases for our course are group 1 metal cations with hydroxide. So that would be lithium hydroxide, sodium hydroxide, potassium hydroxide. Now, there's other things like cesium hydroxide. Cesium is very rare. Rubidium hydroxide, that's super, super rare. You're really not going to see them. The ones that you will see consistently a lot throughout all chemistry courses going into university is the consistent use of these three as a strong base. Now, as a side note, when we're talking about further courses in chemistry, a lot of the times strontium hydroxide is recognized as a strong base, and barium hydroxide is recognized as a strong base. And if you're wondering, well, why is it not necessarily in this course? And the answer is, based on our solubility table, strontium hydroxide and barium hydroxide are low solubility, based on the parameters of that solubility table, which is 0.1 moles dissolving in 1 liter of water. Realistically, they are very close to that, and they do dissociate almost 100% in water and are often considered a strong diprotic base. Next, if I was to look inside of a beaker containing sodium hydroxide and it was labeled as such, realistically, there is no sodium hydroxide. Because it dissociates 100%, really what we have is hydroxide ions and sodium ions completely dissociated as long as we don't go past its saturation point. So the major species for a strong base dissolved in water is really going to be the products only, which are going to be your cation, I'm going to call it X plus, and OH minus. For weak bases, the concept of a proton acceptor makes a lot of sense. Weak bases must react with water in order to form hydroxide. And the basic structure of these reactions look very, very similar, but just almost inverted to a weak acid. So Cn minus, the generic formula for this weak base is A minus, and the generic formula for its conjugate acid is HCN, which is HA. So in a weak base ionization, we're always going to have something plus water making something plus hydroxide. The only thing that's changing out are these somethings. Now, if something is a proton acceptor and protons are H plus, then a weak base has to be negative in some kind of way. So for instance, this is an anion, and most anions, other than the 5 that are neutral ionic, can act as a base. This makes sense because hydrogens, which are positive, are attracted to negatives, and so quite often they will stick onto the negatives. So let's imagine that this here is Cn minus. An H here, if it bumped into this Cn minus, will be really attracted to it. So some of the time, but not all of the time, because weak bases do not go to completion when put into water, some of the time, the water will donate an H plus to this anion in a small percentage. This would then grab onto that hydrogen and form HCN, which is this weak conjugate acid. Again, the reason why this is a small percentage of the time and not 100% of the time is because Cn minus is a weak base. It then produces what's left over, which is hydroxide ion. So it's not that Cn minus has a hydroxide in it, it's that it makes the water turn into a hydroxide ion, this being the hydroxide ion, which is base. So to be clear again, although we call Cn minus a weak base, it really isn't base. The only thing that is truly base is hydroxide. This is base. But we call Cn minus a weak base because when it reacts with water, it creates hydroxide, which is base. So to clarify, when we look back at strong bases, this is not a reaction. Sodium hydroxide is not reacting with water to produce hydroxide. Sodium hydroxide already has hydroxide in it. It is simply splitting into two ions. One of those ions is base. Cn- isn't technically base, only OH- is, but when it bumps into a water, it can tear a hydrogen ion off of water some of the time, creating a hydroxide ion which is left over. This is the base, and therefore we call it a base. Now, you can't look up Kb values in our data book, but what you can do is you can calculate a Kb using a Ka value. I'll explain to you where we get the Ka value in just a moment. I would like to first start by writing out the Kb expression. Kb just simply means base ionizing in water, and the K, of course, is the equilibrium constant for that. So the Kb for this reaction would be HCN times OH-, and this is all over the reactant Cn-. Of course, there's no water there. It's not part of the expression because it's liquid. The generic formulas for HCN, that would be HA, and Cn- is A-. So if I was to write the generic Kb expression for this, the generic Kb would always be HA times OH- all over A-. Now, Ka times Kb is equal to 1.0 times 10 to the negative 14. This is an equation we're going to come across a lot in this course. I'm going to introduce it here. Now, in order to calculate the Kb, I need to know the Ka of the acid in this reaction. So the acid in this reaction is HCN. So what I can do is rearrange the equation for Kb, which would be Kb is equal to 1.0 times 10 to the negative 14. And then I can look up the Ka for HCN. Now the Ka for HCN is 6.2 times 10 to the negative 10. And if you put that in your calculator, you get a calculation of 1.6 times 10 to the negative 5. You'll notice the Kb is less than 1. So weak bases ionize in water or react with water less than 100%. And realistically, they all do it less than 50%. They really favor the reactant side, and there's always going to be more reactants than there are products. So when you looked at a beaker, and this beaker was labeled, I'm just going to throw out, let's say, KCN, aqueous, because there would have to be a cation that it would dissolve in with. The K would come out as K+, which is just a spectator, which I'm not including in here. The major species, the most important species, is actually the Cn-. What you will notice, there is tons of Cn. The Cn is the reactant, and because it reacts very little, the Cn- would be your major species. So the major species in this specific reaction would be the Cn-, and minor species would be the HCN and OH-, but we're really just focused on our major species. So with any weak base ionizing in water, our major species are always going to be the reactants, but we wouldn't include water in there because it's also the solvent. So some terms that you should be familiar with, but we should review, are monoprotic bases, diprotic bases, and triprotic bases. Again, di and tri often get lumped together and are called polyprotic rather than diprotic and triprotic. So generically, a monoprotic base would be a -1 charge. A diprotic base would have a 2 negative charge, and a triprotic base would have a 3 negative charge. So examples would be something like F minus, Cn minus, HCOO minus, but none of the 5 which are neutral. Diprotics could be something like S2 minus, or CO3 2 minus, or SO3 2 minus, or if we're talking about organics that turn into ions, OOCCOO 2 minus. And there's very few triprotics, but PO4 3 minus can be a base. So keep this in mind. Kb is when a base reacts with water. That's what it is. It's not a strong acid reacting with a strong base. It is a base reacting with water. And it will always have this generic setup of blank plus water is in equilibrium with blank plus OH minus. This is for a base. This is Kb. What goes in these blank spots is generically, if we're dealing with just monoprotics, you're really looking at A minus, and this would be HA. Now to summarize this for acids, if I had an acid, it would be blank plus water is in equilibrium with blank plus hydronium. This is for an acid ionizing in water. We call this a Ka. And the only thing that happens is you flip that HA and the A minus. HA goes here and A minus goes there. That's what Ka is. So in summary, the reason why we're looking at acids and bases again in this new unit is that weak acids and weak bases are in equilibrium. Prior to this, you had no idea what equilibrium was, and therefore you couldn't really write out these reactions or understand what a Ka or Kb value represents, which essentially is just the percent ionization in water. Keeping in mind that weak acids and weak bases are going to ionize less than 100% by definition. In actuality, they're pretty much all below 50%. And if we really want to get technical, most weak acids and weak bases wouldn't even ionize 5%. Therefore, most of them favor the reactants less than 50% forwards. We have more reactants than we have products. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.